Alrighty, so here we are, back to process some more constraints. We basically need to set up something that says, okay, so you claim to be a cat deformable. And that's fine, you might be. But the problem that we're going to run into is we might have a constraint that spans two different deformable regions. Like, we want these regions to not be able to break apart. That's what we're setting up now. The thing is, we can have different regions not break apart. Like, we have this whole, thing here. Or put it another way, if I said, how about the cat or rig IDs? So this whole region here, this whole original ID can't break apart. But we don't have to have it attached to this one, attached to this one, attached to this. We don't need it to be one huge thing that can't break apart. We just need to make sure that within an original surface, it doesn't break apart. So we might get constraints between two deformable surfaces, but that doesn't mean that they should be held together. And that's what we need to check for here. Actually, rather down here in our process constraints thing. So we could say, if you claim to be a cat deformable, and that's going to happen, if we have points on two sides of the same constraint and it gets promoted to the primitive, it'll just say, okay, well, the whole constraint is deformable. So we can look. It's like already, if I said, hey, show me all the cat deformable equals 1 guys, check it out. See, the whole thing is connected to each other. Everything is connected as one long cage here. That's no good. So we know what we have to do. We want to see gaps between these things. We want to see gaps between the surfaces where they're not hooked into each other. So I'm going to say, let's find a way where we can, for every one of these lines, for every one of these constraints, let's see if we can see if the actual pieces that are bound together, let's see if they're both from the same cat or rig ID group. Let's see that they both have the same cat original ID. Should be pretty easy to check. What we'll want to do is before we promoted these things, we had cat or rig IDs per point. Each point knew where they're from. When we did this, that actually will get caught up in that and get minimumed, and it'll get wrong. So let's ask the data as it existed before this happened. So hang with me as we go through this. So I'm going to say, what was the original ID 0 of point 0? Because every one of these constraints is going to have a point 0 and a point 1. So we'll say, well, let's start this way. We'll say prim point means for input 0, which is the main input, the leftmost input, of course, and input 1 will be this input. For input 0, for whatever the current primitive that we're working on right now, give me the point number of vertex 0. Like, give me the overall point number of vertex 0. Every prim, remember, every one of these lines will have a vertex 0 and a vertex 1. 0, 1, 0, 1. Everyone's going to have a 0, 1, 0, 1 everywhere. If we look at it here in Geometry Spreadsheet and we look at vertices, you'll see 0, 1, 0, 1, 0, 1. Every single one of these lines has a 0 and a 1 because it has 2 points in it, or 2 vertices in it, I should say. But we want to know what is the actual point number overall so that we can look at this with all 22508 points that it has. I want to look it up in that. So check it out. So prim point of the 0th input, the current primitive that we're working on, vertex 0. That will return me the point number that it is. Now with that point number, I'm going to ask the point and say, hey point, what was your original ID? I know I called it a rig IDs, which is going to keep screwing me up, but oh well. So there you go. So this will work. So this won't error out. So storing into ID 0, and maybe even better for now, I'm just going to actually make it into an attribute just so we can see that it's doing what we want. And this one we just need to change to 1. So now every primitive if we just hide everybody and we'll just look at this ID 0 and ID 1, these were hopefully somewhere in here. Hopefully they're not all 0. Okay, good. The zeros are happening because not everything is a cat deformable in the first place. So if I do this, and let's just look at the ones at 1. So you can see a lot of them, most of them should be the same. But sure enough, we have one here where the ID is not the same. So let's make a little mental note of that. 6882. Let's take a look at 6882. It's like prisoner number 6882. Let's see what's up with that. I'm just going to say pattern 68882. Delete not selected. So here he is. So looked at more abstractly, it's very abstract actually. Let's try something else. Let's look at the pieces here, and let's do that. Not doing anything. Trying to see, I want this to show up like this. It looks like, yeah, so this is pretty good. What we're seeing here is with the original thing here, and then maybe I'll template this one instead. We're seeing a constraint that's connecting the engine, essentially, to the fuselage. So the engine here on the right, fuselage there on the left. So we don't want this to be unbreakable. We don't want this to be a thing that even dents. We want this to just be a whatever. It can be a regular hard constraint so that they're still held to each other, but they're not going to be one of the cool, exclusive, deformable types. So that's what we're going for here. So I'm going to go back to doing it this way. I'm going to say int id1 equals that. So we have the two, and we need to compare them just the way that we just did it, you know, with our eyeballs in the geometry spreadsheet. We'll say, hey, if ID0 is equal to ID1, then we'll do the thing that we were just talking about, where we go from glue to hard to glue again. Otherwise, you are not a cat deformable. You were released from service, like so. So now, when we get over here, we should see that happen. Whereas before, when I said, hey, this is our cat deformables where everything was connected together, now hopefully when I do this, sure enough, they're no longer connected to each other. Now we have these separate islands of things. And this is perfect. This is exactly what we wanted. Great. So here, we don't need to say cat deformable equals 1 because there already is that. So implicitly, we're kind of like, yeah, it is 1, and you get to remain that. But we also want to say whatever you were going to be, you are now definitely going to be a glue instead under this scheme. But you're going to be a glue where as soon as you are broken, as soon as the solver breaks you because you've exceeded your strength, it will immediately, and this is also a built-in type, next constraint name. This is recognized by the solver. It will immediately, in the same time step, turn into a hard constraint, which is pretty cool. So because this is set here, it will know. It will swap this text into here. So it's going to be glue, then it's going to be hard, which will allow it to bend, ironically. And then we ourselves are going to go take this over to the constraint solver and say, but only remain hard for a few frames, then turn back into a glue again. So that's going to be the takeaway from it. Now, if it is one of these things, also, we don't ever want these ones to be clusterable. They should be this glue to hard thing. So I'm going to say else if for this guy. That way it only does clustering if it's not of a deformable type. So that's good. Let's see, what else do we need to do here?